12.4 is going to cover the normal distribution. What you have in front of you is a normal distribution. Notice it says that we have a bell curve. We refer to this as the bell shape curve. And what you need to know about this distribution is normally anything that we make an inference about, where we're doing inferential statistics or making an inference on data values, will be based on this normal distribution. Let's take a look at these histograms. So it states on here the histogram will approach a normal distribution, and it's also called a bell curve or a Gaussian distribution. So when we first initially start on here, our first graph in the upper left-hand corner says this is a random sample of 100 men measuring the height. And then on the vertical axis here, it's measuring the number of men. So that is the frequency. Remember, the frequency will be on that y-axis. So in this case here, look at this first graph, and just by looking at it, it doesn't quite look like that bell-shaped curve. It's not symmetrical. All right, if you move to the right, as we increase the sample size, notice that we start to get a little different shape. It's starting to form the image of that normal distribution or bell-shaped curve. And again, on that third graph, as we continually to increase the sample size, then we have more of a bell-shaped curve. So what we're saying is that as you increase your sample size, your sample will reflect what your population would look like. So it'll come towards that normal distribution. And the last graph, of course, it's saying the normal distribution for a population, which is the bell-shaped curve. And we will find out why it's important to identify that you have a normal distribution in a few slides from now. Let's take a look at this graphical image. So this has three curves on the same basically coordinate system, if you will. And when you take a look at this, all three graphs have the same mean. So their x-bar is the same for all three curves. All three curves are symmetrical. That's following a normal distribution and considered a bell-shaped curve. The difference on these is the fact that their standard deviation is different. So the green graph is very narrow, very tall. So all your data is close to that mean. So therefore the standard deviation is small. There's less variability away from the mean. As we go to the blue graph, you're getting a little bit wider. So therefore the standard deviation is a little bit higher, a higher number, and it has a little more variability. When we look at the burgundy or red graph, you can see that if you're looking at the mean, it's very wide. So that's telling you that has an increased variability, the highest standard deviation out of the three graphs that you see. So when you look at graphs, you want to look at the standard deviation to see if it is a large number, does it have a lot of variability or dispersion. This next slide is really important. It is showing you the 68, 95, 99, 7 rule for the normal distribution. Again, the normal distribution is when we identify that we have a nice bell-shaped curve and our population is being represented well by the sample size that we have selected. So on here, it says that approximately 68% of the data falls within one standard deviation of the mean, and it means both directions. So both directions mean above the mean to the right or below the mean to the left. So you can see on here, they just labeled our x-axis with like a number line from -3, -2, -1. The 0 right there is going to be considered our mean. That's my x-bar is the 0. If I want to look at one standard deviation above the mean, that is the number 1, a little square around it. And one standard deviation below the mean will be represented by this -1. All right, so it's saying in that pink area on the graph, that area underneath the curve is representing 68% of our data items. All right, thing you need to remember about this bell-shaped curve is that it holds 100%. I'll write this up there, holds 100% of your data. Of course, we need to have all our data set represented when we display a graph. Now, although the graph looks like it's stopping at -3 and 3 or close to it, it actually doesn't. This graph continues on and gets really close to that, what we call x-axis or the horizontal line, but it never touches or crosses it. It just slowly approaches it. So we actually do have some values that are less than -3 or greater than 3 on that graph. It's just not showing everything at this point, but you have to know it holds 100% of your data. So taking a look at the next part, we have approximately 95% of the data that falls within 2 standard deviations of the mean. So in this case here, you're looking at your -2, the area under the curve between -2 and 2. So this is going to include that pink area in the middle and also the blue areas. And that is going to give you 95% of your data will be represented between the -2 and 2. Lastly, approximately 99.7% of your data items fall within 3 standard deviations of the mean. So in this case here, we're going to look at the -3 and the +3. And your graph underneath the curve is represented by 99.7%. All right, so if 99.7% is falling within 3 standard deviations of the mean, that's leaving you 100% minus the 99.7%, and that leaves you 0.3% that will be represented on those areas that are above 3 and below the -3. So we will follow this rule, the 68, 95, 99, 7, in dealing with the normal distribution. Let's look at this example. Male adult heights in North America are approximately normally distributed, which is really important for us to keep in mind, normal distribution, with a mean of 70 inches and a standard deviation of 4 inches. Find the height that is 2 standard deviations above the mean. All right, so let's write down what we were provided. We know we have a normal distribution, so we're looking at a bell-shaped curve. Our mean, or x bar, is 70, and our standard deviation, S of x, is going to be 4 inches. If we look at our solution region, it's telling us the height is going to be equal to the mean plus 2 times the standard deviation. So this will give us, inserting our values, 70 plus 2 times 4, or a height of 78 inches. So 2 standard deviations above the mean is represented by 78 inches in height. All right, another way to look at this is to take our mean, add 1 standard deviation, add your second standard deviation, and that will still give you 78 inches. Just a different take on it, however you wish to set up your problem. The second part on part B says 3 standard deviations, and it's going for below the mean. So if it's above the mean, we add. If it is below the mean, we subtract. So for B, it says the height is the mean minus 3 times the standard deviation. So that would leave you with 70 minus 3 times 4, or an end result of 58 inches. And again, the other way to look at this is your mean of 70 and then subtracting 4 3 times to get to 58. So this image is demonstrating what it would look like if we made our normal distribution given that previous problem we had. So remember, it said the mean is 70 and it gave us a standard deviation of 4. So what we found on the previous problem is that we came out with the 78 inches, which was 2 standard deviations above the mean. And then we also came up with 58 inches, which was 3 standard deviations below the mean. So what you would do if you made your own graph is you would go ahead and draw your bell-shaped curve, and you put your mean or your x bar right in the center, that's your 70. If you add one standard deviation, 70 plus 4, you're going to get 74. You take the 74 and add another 4, you'll get 78. You're now at 2 standard deviations. And add another 4, and you'll get 3 standard deviations, the 82. In the same sense, if we go in the opposite direction, we will subtract. So going to the left of 70, 70 minus 4 will give you 66. 66 is representing 1 standard deviation below the mean. 66 minus 4 gives you 62, 2 standard deviations below the mean. And then we already know our 58 is representing 3 standard deviations below the mean. All right, so we're going to go plus or minus out to 3 standard deviations when you draw a bell-shaped curve. Notice that because it's a normal distribution, we're able to use our 68, 95, 99, 7 rule. Still continuing with our example of the percentage of men in North America with heights, we're looking at our same bit of information. We have our X bar is 70, that's my mean. Standard deviation is 4. All right, so part A is asking us to find the percentage of men in North America with heights between 66 inches and 74 inches. So once again, let's look down at our graph, our normal distribution, and we're looking for between 66 and 74. So if you recall, if you are within 1 standard deviation away from the mean, above the mean and also below the mean, we're looking at all this area in red, and that is following the rule of 68, 95, 99, 7. So the area under the curve between 66 and 74 is going to be a total of 68%. So part A will give you the answer of 68%. Now for part B, it says between 70 inches and 74 inches. So if we're looking at between 70 inches, which is the mean, and the 74, which is 1 standard deviation to the right, we're basically looking now at just half of that 68%. All right, half of that 68%. So for part B purposes, we're going to take the 68%, divide it by 2 or cut it in half, and that will give you 34%. All right, so the percentage that represents the men in North America with the heights would be between 70 and 74 inches would be 34%. This slide just reviews what I went over on that part B. So again, we took our 68%, divided it by 2, and we came up with an answer of 34%. So for part C, it's asking you to find the percentage of men with heights above 78 inches. So when we look at our graph this time, if you're at 62 and 78, you are 2 standard deviations above and below the mean. All right, so that means that that area under the curve between 62 and 78 is going to be 95%. So knowing that that part of your curve is 95%, that leaves the rest of this data over here to the left, which is below 62, and the area to the right of 78 inches. That's going to be the remaining 5%, because remember, under the curve is 100%. So we have 100% minus 95% will leave you 5%. Now, 5% goes for both ends of the graph. We only need to know above 78 inches, so we only want to know one side of it. So we're going to take that 5%, divide it by 2, and you're getting 2.5%. And this 2.5% represents one end, and that would be our final answer. So once again, the area under the curve is 100%. Knowing the area in between 62 and 78 is represented by 95%. We subtract 95 from 100, we get 5%. 5% represents both ends of the remaining part of the graph. We divide that amount by 2, we get 2.5, which represents only one end. So therefore, the 2.5% is the percentage that represents the men, the height of the men, above 78 inches. So let's practice. The scores on a test are normally distributed with a mean of 120 and a standard deviation of 24. A score of blank is 1 1/2 standard deviations below the mean. All right, important thing that we want to know is the normally distributed, mean of 120, standard deviation of 24. So let me just write this out. I have my X bar and I have my standard deviation. All right, so it's asking for 1 1/2 standard deviations below the mean. So below the mean means we're going to be subtracting. So we could think of it as taking our mean minus 1 standard deviation and then minus 1/2 of a standard deviation. If we fill in our values, we will have 120 minus 24 minus 1/2 of 24, or you can see it as 24 divided by 2. That would be considered your 1/2. And we'll just keep going here with our problem. And that will give you a total of 84. All right, so again, this is 1 1/2 standard deviations below the mean. Therefore, we will be subtracting from the mean. The figure illustrates a normal distribution for the prices paid for a particular model of a new car. The mean is 12,000, standard deviation is $500. And they give us a nice hint: use the 68, 95, 99, 7 rule to find the percentage of buyers who paid between $10,500 and $12,000. So remember, we're finding a percentage, so that's that area under the curve. So they already drew out the normal distribution curve for us. The mean is in the middle at 12,000. That's my X bar. And they added standard deviations to the right of the mean, and they subtracted standard deviations to the left. Notice that they want us to find the percentage of buyers who paid between $10,500 and $12,000. So $10,500, if you take a look, it is 3 standard deviations below the mean. All right, knowing that it is 3 standard deviations below the mean, what we can do is we follow our rule of thumb, and it is representing 3 standard deviations above and below the mean. All this area right here is going to be considered 99.7%. Now, all we want is between 10,500 and 12,000. So we're only looking at half of that area instead of all of 99.7. We only want half of it. So we're going to take the 99.7%. We're going to divide it by 2, and that will give us 49.85%. So in this case, 49.85% is representative of the buyers who paid between $10,500 and $12,000. Not everyone pays the same price for the same model of a car. The figure illustrates a normal distribution for the prices paid for a particular model of a new car. This time the mean is $18,000. Standard deviation is $2,000. Using the 68, 95, 99, 7 rule, find the percentage of buyers who paid less than $12,000. So in this case, they're using the 18 in the middle here as X bar, my mean, and we want less than. So if you take the 18,000 And again, you add 2,000, you'll get to the right to the 20,000, the 22 and 24. They're just adding increments of 2,000. If we go to the left of the mean, they're subtracting 2,000, so it drops to 16 to 14 to 12. There's that number 12 we want that's representing $12,000. It wants to pay less than. So we're actually trying to find this area under the curve that falls to the left side or less than the $12,000. All right, so keep in mind once again, that number 12 is 3 standard deviations away from the mean. Let me mark that so it'll make sense to you. This is 1 standard deviation below the mean, 2 standard deviations, 3 standard deviations. And because it is 3 standard deviations below the mean, or you can say within 3 standard deviations, I can go over here and look at the 99.7 once again, because all of this will reflect the area under the curve plus or minus 3 standard deviations away from the mean. So I'm looking at all this area between here and here. And that's going to be 99.7. So again, if I'm looking at a tail end, and there's 2 tail ends here, there's still some area over here that's also represented under the curve. We just can't see it well. All right, we need to take 100% minus what we do have. We do know the 99.7%, and that's the area between $12,000 and $24,000. And that will give us 0.3%. Right? Once again, this is representing both ends. But we only want less than 12,000, so we're just wanting this side that's lower than 12,000, or to the left of 12,000 on our curve. So therefore, we're going to take that 0.3 divided by 2, and we're going to get 0.15 or 0.15 of a percent. And that will represent one end. And that would be our final answer that we would place in is our 0.15% are the buyers that pay less than $12,000. So if you want to check this, what you would know is that if you look back at the graph on the very top, we have the 99.7%. On the left of that, this would be the 0.15%. And over on the right-hand side, greater than 24 would be the other 0.15%. So if we were to add all those values together, it should equal to a total of 100% of our data. Scores on the GRE or the Graduate Record Examination are normally distributed with a mean of 523 and a standard deviation of 145. Use the 68-95-99-7 rule to find the percentage of people taking the test who score above 668. All right, again, some key words in there. Normally distributed. So we think of our bell-shaped curve. Mean of 523, that's my X bar. And standard deviation, 145. We're going to use our rule of thumb there, 68, 95, 99, 7. And they want us to focus on the percentage of people who take the test who score above 668. So again, we need to probably, something that would help us is identify what's given, but also maybe perhaps draw that bell-shaped curve and see if we can label it. All right, so I have X bar, which is 523. Standard deviation, 145. Again, we are going for above 668. So if I were to draw my curve out, and pardon me, because I know my curves are always kind of strange looking, we'll say this is my bell-shaped curve. All right, so right in the center here is about so. So that would be my mean, or my 523. All right, and then I want to go equal distance out here. One standard deviation to the right, 2 standard deviations, and 3 standard deviations. All right, we don't have to label all of these, but I'm just marking them down so you know. This is going out to 3 standard deviations to the left also. So since I know that this score is 668, 668 is greater than the mean, that is 523. So I'm going to take 523 and I'm going to add 1 standard deviation to it and see what I get. When I add these two together, we get 668. So just by chance, our 1 standard deviation above the mean is going to give you 668. So I'm going to leave it like that. Now I have to identify again, it wants above. So I'm going to make an imaginary line right here, or try to, and it wants this area that is greater than or above. So we want to find all this percentage that is to the right of 668. All right, so once again, that we had identified was the fact that we can use that rule, and we know by the rule that, let's add this together right here, whoops, that 1 standard deviation is 68%, if we remember correctly here. All right, so we know that 68%. So if we're going outside of that 68%, we have 2 tail ends. We have above the 668, that's 1 standard deviation, and we also have to the left. Both of these represent both ends. So what we're going to do in this case is we're going to take the 100%, since that's the total area under the curve, minus the area that represents within 1 standard deviation, the 68, and that'll give us 32%. The 32% represents both ends. All right, and that's the part I circled on our distribution graph. And then since we only really want this one side over here, the side that represents the greater than 668, what we need to do is take that 32% and divide it by 2. And now when we divide by 2, we will get 16%, and that will represent each of the ends, right? So in this case, the percentage of people that take the test to score above 668, this whole area under the curve is going to be 16%. All right, so 16%. That is all this dark shaded area under the curve. A new concept, computing z-scores. So a z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. All right, and the formula for a z-score is taking your data item minus the mean, all divided by the standard deviation. So I'll rewrite this in symbology. Our data item is x, and our mean is x bar, so x minus x bar, divided by the standard deviation, s of x. Data items above the mean have positive z-scores, and the data items below the mean have negative z-scores. The z-score for the mean is 0. So one of the things you need to know is when you find a z-score, normally we would refer you back to a table or a chart that has a listing of many z-scores, and underneath each of those z-scores, it'll refer you to, in decimal form, the area under the curve. All right, so we've already been working with area under the curve in percentage form. On the z-score table, it gives it to you in decimal form, which is easily convertible into a percentage. So let's see if we can kind of draw a normal distribution and make sense of this. And not so great on the bell-shaped curve yet, but we'll keep working on it. All right, so in the center would be your X bar. And remember, as we go out, we're moving out 1 standard deviation, 2 standard deviations, and 3 standard deviations. And we'll also go out to the left or lower than the mean. And I didn't quite draw that long enough, so there we go. So if I had to list this in the sense, this is my x's or my data value. To the right of the mean is x bar plus 1 standard deviation. Then I have x bar plus 2 standard deviations. So we're going to the right means we add, and I'll get out to the 3 standard deviations. If we go to the left, we subtract. So it's x bar minus 1 standard deviation, x bar minus 2 standard deviation as I'm moving out to the left of the mean. And the last one's going to be x bar minus 3 standard deviations. All right, once again, this axis here is representing the x, or you can say your data values. In this case here, the term is data item according to that formula, my x's. All right, instead of redrawing this curve again, what I'm going to do is relabel that graph, and you would replace that number line with this number line. And now we're looking at z-scores. All right, the z-score, on the z-score, the mean is equal to 0. 1 standard deviation above the mean is just a 1, so it's looking like a number line. 1 standard deviation below is going to be -1. We go to -2 and -3. All right, so you can use these scores just like we did previously with our rule of the 68, 95, 99, 7 rule to find the area under the curve. So let's look at this example. The mean weight of a newborn infant is 7 pounds and the standard deviation is 0.8 of a pound. The weights of newborn infants are normally distributed. Find the z-score for a weight of 9 pounds. Okay, so we're looking for a z-score. Let's look again what they gave us. The mean weight is 7 pounds, so x bar is equal to 7. Standard deviation is 0.8. And it says find the z-score for the weight of 9 pounds. So this 9 pounds is your data value, or x. All right, so looking down in the solution region, they're using your formula for the z-score. So it has z sub 9. So z is equal to x minus x bar divided by the standard deviation. That's our formula. Again, so they took 9 minus the 7 divided by 0.8, substituting in our values. And they came up with a value, or a z-score, of 2.5. All right, you may have noticed on the left side it says z sub 9. That's just telling you your data value of 9, the z-score when the value is 9. So it says on here a 9-pound infant is a chubby little tyke with a weight of 2.5 standard deviations above the mean. All right, so if you remember what I said earlier, if you are over 2 standard deviations away from the mean, that's considered unusual. If you're more than 3 standard deviations away from the mean, that is considered very unusual. So being that this one is 2.5 for that deviation, I would say that this is considered an unusual weight for a baby, considering that our mean is 7 and our standard deviation is 0.8. Keeping with the same problem, with the mean weight of the infant of 7 pounds, a standard deviation of 0.8 of a pound. This time we're asked for the z-score for the weight of 6 pounds. So 6 pounds is our data value, or x. Substituting in our values into the z-score formula, we get 6 minus 7 divided by 0.8, and that's going to give us a negative 1.25. So remember, if it's negative, it's going to be the left side of the mean. So this one's read to you as 6 pound. Infant weight is 1.25 standard deviations below the mean. So this is a graphical image of the last two slides that we completed, dealing with the weights of newborn infants. Using the normal distribution, a graph was created. At the top, you have your mean here of 7. And if you do your plus or minus your standard deviations, you'll get these other values. These are the weights or the X values for the infants. Now, right below it, they place the Z-scores that correspond to those weights. So you can see that we have all the way through to -3 to 3 for the Z-scores. Our 9-pound infant is represented over here on the far right, and our 6-pound infant is represented right here on the left side. That was our -1.25 standard deviations below the mean. Scores on a dental anxiety scale range from 0, no anxiety, to 20, extreme anxiety. The scores are normally distributed with a mean of 11 and a standard deviation of 4. Find the Z-scores for the given score on this dental anxiety scale. 8. All right, so we know that we have a normal distribution. Mean is 11, so X bar is equal to 11. Standard deviation is 4. There's my S of X is equal to 4. And it says the given score, so that 8 is your given score. That is your X value. Find the Z-score. So I'm going to locate Z sub 8, evaluating it, my data value. I have 8 minus 11 divided by my standard deviation of 4. And when I place this in my handy dandy calculator, I get a -75 hundredths. All right, so this is telling me that that score of 8 is 75 hundredths standard deviations below the mean. All right, 75 hundredths of a standard deviation below the mean. Intelligence quotas on two different tests are normally distributed. Test A has a mean of 100, standard deviation of 15. Test B has a mean of 100 and a standard deviation of 12. Use Z-scores to determine which person has the higher IQ, an individual who scores a 135 on test A or an individual who scores a 123 on test B. So let me write this down separately first. We'll have test A over here on the left side. And test A, we have a mean of 100, standard deviation of 15, and they gave us a test score that was 135. And I'll put test B over here on the right side. Now test B had a mean of 100, standard deviation of 12, and X, its test score is, let's see, it was 123. All right, so it says use Z-score to determine which person has the higher IQ. So we need to go find the corresponding Z-score for each of those scores on the test and then compare them. So remember, to find our Z-score, we're going to go Z sub 135 is equal to my X value, 135, minus the mean of 100, divided by the standard deviation. And if I go ahead and place this in the calculator, I will get 2.33. So 2.33 is my standard deviation above the mean for test number A's score. And then when I take a look for test B, I'm going to have my Z sub 123, which is equal to 123 minus the mean of 100, divided by 12. And this one will give me a score of 1.92 standard deviations above the mean. So since they're both positive, they're above the mean. The one that is farther away from the mean or farther away to the right of the mean would be the one that has the higher IQ. So in this case here, the one that has a 2.33 or the score of 135, test A, would have the higher IQ. So we would choose answer A. The individual who scores 135 on test A has the higher IQ. And right below this is basically all the same information, just reiterating to you what the standard deviations are. So again, we are reminded of the formula for a z-score. It says a z-score is the data item, which is my x, minus my mean, x bar, divided by the standard deviation, s sub x. And this problem's asking us, it says a set of data items is normally distributed with a mean of 400 and a standard deviation of 50. Z is equal to -8. And it says the data item that corresponds to Z is equal to -8 is. And then it tells us to type in an integer or a decimal. So it's telling you the item, the data item, you're looking for X in this case. So once again, I'm going to write this out. Z is equal to X minus X bar divided by standard deviation, S sub X. We're going to substitute the values that we do know. We do know that Z is -8. We don't know what X is, so we'll leave that where it's at. Our mean is 400 divided by our standard deviation of 50. So once again, all we did was substitute in the information that we know. So the idea is that you have to find your data items. So you are going to solve this equation for X. The first thing you do on here is to get rid of your denominator. Since this says divide by 50, the opposite of divide is to multiply. So we will multiply this right-hand side by 50, and we're going to multiply the left-hand side by 50. Once again, we do this to eliminate that denominator, so we'll divide that out. As we work this, 50 times -8 is -400, now equal to, and we are left with x minus 400 on the right-hand side. We will continue to focus on isolating x. So since I have a -400, I need to do the opposite operation, and we will add 400. What you do to one side of the equation, you must do to the opposite side. So again, on the right-hand side, this will eliminate my 400. So on the left side, though, it also eliminates the 400. -400 plus 400 will give you 0, and that leaves you x. So in this case, our data item is going to be 0. We are now going to look at a different variation of our curves. The first one, if you notice that we have the right-hand side, it sort of tails out towards the right. So this is called skewed to the right or right skewed. When it is right skewed, notice that you have your mode, median, and the mean in that order for it being right skewed. If we look at our second graph, this tail end kind of drags over towards the left side. So this is called skewed to the left or left skewed. And in this case, the order is the mean is first, then the median, then the mode, if you're reading it from left to right. So different variation of our curves. This is a right skewed and a left skewed. There are 50 states in a certain country. The histogram shows murder rates per 100 residents and the number of states that had these rates in a certain year. Use this information to complete parts A through E. So it has a title, Murder Rates per 100,000 Residents by the State. On the vertical axis, you can see that we have the frequency listed. And then on the horizontal axis, that's going to be the rates that they have listed. So question A is the shape of this distribution best classified as normal, skewed left, or skewed right? So remember the normal distribution, that's that bell-shaped curve. This is definitely not bell-shaped curve. Now, this is not a perfect skewed graph, but it is closer to being a right skewed, which would look something like this, and then it drags out off towards the right. So this would follow suit with answer number C, skewed right. The next part is going to ask us to find the mean. In order to find the mean, what we have to do is to take each rating and multiply it by its frequency. And this will be written out for us on the next screen. So we are using, for instance, the rating of 1 is going to be multiplied by 4, plus we'll take the rating of 2 and multiply it times its frequency of 6, and we'll go so forth. We'll add all those together and divide it by the number 50, or representing the 50 states. And then we'll find the mean that way. And I'll show you that on the next page. They also are asking you to find the median. So part C, this can be a little more challenging. Finding the median. If you remember, the median is listing your data set from smallest to largest and finding the middle number. Since this data set represents 50 states, what you have to remember is you have 50, and that's an even number. So on an even number, that means we have to take the average of the two middle numbers to find the median. So 50 divided by 2 is equal to 25. So we're looking at what numbers are in the 25th and the 26th position of this data set. All right, again, we're finding the median. So these ratings are already listed from smallest to largest on this graph. We need to take a look and find where's 25 and 26 positions fall at. So starting with the far left, I have frequency of 4, frequency of 6. I'm just going to add these together, try to get close to 25 and 26, and plus 9. All right, so if I just stop right there looking at those first 3 ratings, I have 19. I'm not quite up to this 25 mark that I need. So that means that I have to go from the first 3 ratings of 1, 2, and 3. I need to go above rating 3 to the rating 4. Now, rating 4 has 8 frequency of 8. So it means 4 is listed 8 times. So if I add 8 over to that value of 19, now I'm getting 27. Well, 27 is higher than 26. So that means the 25th and the 26th position will fall under the rating of 4. So your median is going to be the number 4. And we'll discuss this further on the next slide. So once again, continuing, it says calculate the mean murder rate per 100,000 residents for the states. And you can see on here that I had written out finding the mean. You have to take the summation of, and this is part of our old formula, it had X bar is equal to the summation of your data value times its frequency. And we had to add all of those together, those products together, and then we had to divide it by N, which is the number of states we had. All right, so I wrote down all this craziness. Every score, the rating is the 1, 2, 3, 4, 5, all the way out to 12, times its corresponding frequency. If you place this all in your calculator, divide by 50, you'll come out with the mean of 5. All right, and then on part C, we looked at that already. We know we have the 50 states, and so we would have 50 numbers listed from smallest to largest. And out of those 50 numbers, the halfway mark would be between the 25th and the 26th number. All right, and we found that the 25th and the 26th number falls under the rating of 4 because that number 4 was listed 8 times. That was the frequency for the rating of 4. It was listed 8 times. So that means the 25th position had a rating of 4, and the 26th position had a rating of 4. The idea on the median is to take the two middle numbers, add them together, divide by 2, and you will get your median, which gave us 4. Once again, this is the median, middle number. So that is how they came about this answer right here. All right, and then lastly, it says on here, are the mean and median murder rates consistent with the shape of the distribution that you described in part A? Explain your answer. So you can see that the mean, which is 5, is greater than the median, which is 4. Again, the mean is greater than the median. Remember, we talked about this. We said that this is considered a skewed right graph. So let me see if I can draw that again, and it skews. All right, and on a skewed right, remember we had it where it was listed. It was mode, then it was the median, and then it was the mean from left to right. So remember, if you're to the right, it's a larger value. So this would make sense that my mean is to the right of or larger than the median on a right skewed graph. So we're saying that the mean is greater than the median, so therefore it does follow suit that this is a skewed right graph.